Hello everyone, this is my 18th lecture and in this we shall discuss about the application of Gauss theorem. The first application of Gauss theorem was the electric field intensity due to uniformly charged infinitely long straight wire. Now it is the second application, electric field intensity due to uniformly charged infinitely large sheet. And for the case we shall calculate or we shall determine the direction of electric field intensity due to charge sheet, and then after we shall calculate the magnitude. So first of all we consider an infinitely large sheet. And it is uniformly charged. Its A area contains Q amount of charge, and we shall calculate the electric field intensity at a certain distance R from P. So first of all we shall calculate the electric field intensity and its direction, and for the direction we divide the whole sheet into a very small area elements, and we consider two area elements at equidistance from the point P. Let this is a small a, shall consider this is A and this is B. This angle is theta. This angle will also be theta because equidistance are there. And now again we increase this and this one. This will be DEB and this will be DEA. Electric field intensity, direction of electric field intensity due to element area A and electric field intensity due to element area B. If this angle is theta, then this angle will also be theta because vertically opposite angle. This angle is theta and this will also be equal to theta, vertically opposite angle. Now we will resolve DEB and DEA into their components. Here we shall obtain DEB cos theta and DEB sin theta, and in this case DEA cos theta and DEA sin theta. After resolving DEB and DEA into their components, their cos components are along same direction and their sine components are equal in magnitude and opposite in direction, so they cancel out. And only due to cos components the electric field direction of electric field intensity can be decided. And in this case, for a positively charged plate, the direction of electric field intensity will be vertically outward direction, and for negatively charged plate the direction of electric field intensity will be towards the plate perpendicular to its plane. So these are the direction of electric field intensity for the case, and in this manner we can determine the direction of electric field intensity. Again I am explaining. First of all we consider a point P at a certain distance R, then we consider two element areas and then A and B, and then the direction of electric field intensities due to element area A and B are DEB and DEA. They are resolved into components, and then their cos components are add up and sine components are equal in magnitude, opposite in direction, so they cancel out. And then we shall calculate the, in this manner we can determine the direction of electric field intensity due to positively charged sheet the electric field intensity direction has the vertically upward direction and towards the sheet, away from the sheet is there. Now in order to determine the direction, magnitude of electric field intensity due to sheet, we consider a charge sheet this is a positively charged sheet, and then we consider a cylindrical Gaussian surface. This is a cylindrical Gaussian surface. The corresponding charge is Q, corresponding area is A, and here will be the surface S1. The direction of electric field intensity will be along this direction, and this is the surface S2, and direction of electric field intensity will be along this direction, and the third surface is third surface, and the direction of surface area is dE, and electric field intensity will be this direction, and this angle is 90. Here the angle between surface area and electric field intensity is 0 degree, and here is also 0. Consider an infinitely large, uniformly charged sheet of which area A contains Q charge. Consider a cylindrical Gaussian surface. Consider a cylindrical Gaussian surface. This is the Gaussian surface, and Gaussian surface always a closed surface, and it has electric field intensity at its every point. These are the two conditions for the Gaussian surface. So we apply the Gauss theorem. From Gauss theorem, we know that the mathematical form of Gauss theorem is electric flux, the net outward electric flux is equal to the ratio of summation Q, means algebraic sum of all charges, to the permittivity of vacuum. So we divide this, this is for closed whole surface. Now we divide it into three surfaces. Surface S1, E, dA cos 0, for surface S2, this surface, E, dA cos 0, for surface S3, E, dA cos 90. This is equal to Q upon epsilon. So this is E can be taken out, because at every point of Gaussian surface electric field intensity is same. So we can consider it as a constant, and E into dA plus E into dA plus due to cos 90, this value will be equal to 0, is equal to Q upon epsilon. If the area of these circular surfaces will becomes equal to the area of this sheet, then E into A plus E into A is equal to Q upon epsilon naught. 2E into A is equal to Q upon epsilon naught, and electric field intensity is equal to Q upon 2 epsilon naught into A. And Q Q by A is equal to sigma surface charge density. So E is equal to sigma upon 2 epsilon. Area is small a, we have considered it. So this is A, this is also A, this is A, and sigma upon 2 epsilon naught. This is the electric field intensity due to infinitely large uniformly charged sheet. Here we know that the E is independent of R. So if we want to draw the curve between E and distance, it will be a line parallel to distance axis. So this is the electric field intensity due to uniformly charged and infinitely large sheet. Now we shall discuss about the 2-3 more points that if we consider two uniformly charged infinitely large sheets placed very close to each other, then what will be the electric field intensity at outside each plate and between the plates? For the case, we can consider the first case. If both sheets are positively charged, this is also a sheet. These are the two sheets, and that we consider the surface charge densities are equal, both are positive, and now we have to calculate the direction of electric field intensity at point A, at point B, and at point C. This plate is P and this plate is Q. Now, at this point, because we know that the electric field intensity is independent of distance, so the electric field intensity at this point due to this plate and this plate both are equal. And in this case, the value will be EP, means electric field intensity due to this point, this plate, and electric field intensity due to this plate both are along same direction, so they add up. And the value of EA will be is equal to EP plus EQ, means sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught. So sigma upon epsilon naught will be the electric field intensity. Similarly, at this point, the value of EP and EQ are also along same direction, and magnitude is same. So at EC is equal to EP plus EQ sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught, means sigma upon epsilon. And in between, here is the direction of EP and here is the direction of EQ, and the value will be EB is equal to EP minus EQ, means sigma upon 2 epsilon naught minus sigma upon 2 epsilon naught is equal to 0. So at point A, the electric field intensity will be sigma upon epsilon naught. At this point, the electric field intensity will be sigma upon epsilon naught, and between the plates it will be 0. The similar result can be obtained for two negatively charged plates, but the direction of electric field intensity will be changed. Both are negatively charged plates. This is P plate, this is Q plate. The surface charge density is minus sigma, we consider the equal. You may consider the different also. This point is A, this point is B, this point is C. Here the direction of electric field intensity EP due to plate P and EQ both are along same direction. The value will be same, just as EA is equal to EP plus EQ is equal to sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught is equal to sigma upon epsilon. And the direction will be towards the plate. At the point C, the direction of electric field intensity also will be same, EP and EQ, and EC is equal to EP minus plus EQ, means similarly sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught, and the total value will be sigma upon epsilon. Between the points, the electric field intensity EP will be towards the plate P, and electric field intensity EQ will be towards the plate Q. Both are equal in magnitude, opposite in direction. So at point B, EP minus EQ means again sigma upon 2 epsilon naught minus sigma upon 2 epsilon naught is equal to 0. And the last case, if the electric field, the plates are charged by opposite charges. One plate is with positive charge and other one is negative charge. In this case, we consider again the sheets, two sheets. This is positively charged plate, P plate. This is a negatively charged plate. Plus sigma minus sigma. Here also we consider point A, point B, point C. The direction of electric field intensity due to plate P will be along this direction, and plate Q towards the plate Q. Both are opposite. So EA is equal to EP minus EQ. And value we have sigma upon 2 epsilon naught minus sigma upon 2 epsilon naught is equal to 0. So at this point, means outside one side of the plates is electric field intensity 0. In this case, electric field intensity due to EP, this is EQ, and EC is equal to sigma upon 2 epsilon naught minus sigma upon 2 epsilon naught, and it will be equal to 0 because EC is equal to EP minus EP. Now we shall discuss about the at point B between the plates. The EP will be away from the plate and EQ will be towards the plate, so both are along same direction, and EB is equal to EP plus EQ and sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught. So between the plates, electric field intensity will be equal to sigma upon epsilon. These are the three special cases in which we consider two separate plates, charge plates, and then we shall consider the direction of electric field intensity and magnitude of electric field